Welcome. In this video, you'll learn what a learning curve is in machine learning terminology, where to find the learning curve for your project in DataRobot, how to calculate additional sample sizes on the learning curve, and generally how to interpret the chart. The skills you learn in this short video will help you make decisions about the amount and type of data that you need to solve your problem. It will also help you manage expectations among stakeholders as to the final accuracy of your model and make choices about how much data to use for model retraining to balance computational time versus accuracy. First, let's define a learning curve, also known as a training curve to some data scientists. The learning curve is a plot of the error metric on the vertical axis versus the amount of data used for training on the horizontal axis. The plot is useful to show the relationship between more data and model improvement. In the real world, data scientists generally observe that more data is better up to a point, after which more is just more, and the addition of more data no longer makes the model better, and could even make it worse. The learning curve plot helps you answer the question, will more data improve my solution? When I look at a learning curve, I mentally extrapolate it to the right, and I ask myself, what would happen if I add more data? How much better is my model going to get, and is that amount of improvement worth that additional amount of data? So keep that mental extrapolation in mind as we look at some examples. The first example is from a computer vision project to classify skin lesions. We have about 10,000 images and diagnostic codes in one of 7 categories, including some which are cancerous and non-cancerous. For each, we have an image associated, which we will attempt to classify into those 7 categories. Let's take a look at the learning curve for this. Here we see multiple learning curves plotted on top of each other for the various blueprints that DataRobot has tried at sample sizes going from 8% up to 64% of the total data. Computer vision tasks are known for requiring large training sets, especially when it's required to learn fine details in the images. So going from this group of models at 32% to this group of models at 64%, we still see a substantial improvement in log loss here on the y-axis. The correct conclusion is that more skin images will continue to improve the model and are probably worth collecting. This model hasn't achieved maximum performance yet, and the use case of identifying cancer is one where model accuracy is of paramount importance. Of course, there's also a cost to obtaining the data and having it expertly labeled by physicians. Let's take a look at another example. This one is from the airline industry to predict in a binary way whether a flight will be delayed by 15 minutes or more. We have 50,000 data points, including information such as the carrier and the flight date. Let's take a look at the learning curve. At first glance, the learning curve looks similar to the skin lesions example, but look carefully at the y-axis labels. The total range plotted is from 0.58 up to about 0.61. This learning curve is actually fairly flat, but that won't kind of pop out of the chart unless we add a few more sample sizes. To compute the learning curve for other sample sizes, click on the models that you wish to include, either in the chart or in the legend, and then choose Compute Learning Curves. Here I'm going to replace these values with 8%, and 4%, and hit compute. We'll wait for that to finish while these modeling workers kick off. Great, our 8% and 4% calculations are done, and while I was at it, I actually added some 2% and some 1% calculations as well. This really makes the point that even with 1% of the data, which would be 500 rows, the log loss is 0.64. All the way up at 64% of the data, our log loss is still about 0.58. This is an example where a very small amount of the data actually has taught the model quite a lot, and it's debatable whether adding more rows is the right way to proceed. What you may not have noticed is that the original data actually has no weather information whatsoever at the origin or the destination. So rather than adding more rows, probably suggests that this team focuses on collecting some additional information such as weather. Before we leave learning curves, let me share a true story from a POV with a retail client. That client was trying to upload a data set with 2 million customer records, and that was taking some time to complete. Since the purpose was really to learn the DataRobot interface, I suggested we proceed with 2,000 rows. What you're seeing on the left here is the actual learning curve from those 2,000 rows, which was only 0.1% or 1/1000th of the available data. The learning curve was already flattening out. Working with the whole data set of 2 million records, which she had been doing in Python in some enterprise notebooks, was a complete waste of compute resources and was greatly extending her time to insights. Based on this learning curve, something in the range of 20,000 rows, which is 1% of her available data, would have optimized the accuracy versus model training speed, especially since she intended to repeat this every 2 weeks. After watching this video, you should be able to find the learning curve in DataRobot and use it to compute additional sample sizes not already plotted. You should also be able to interpret the shape of the curve to conclude whether there's utility in gathering additional data and be able to communicate to stakeholders what the maximum performance from the current features is likely to be. In cases where data is very plentiful, you should be able to use the learning curve to decide how much data to use for training to reduce computational time while retaining model accuracy. See you next time.